Hello, in this section I will talk about pipeline fundamental and give a bin to BCD design example. Okay, this is the content. First, I will talk about the benefit of pipeline. Then we will study pipeline from an example. That is the bin to BCD example. I will first introduce the design requirement, then I will analyze the algorithms we can use to solve this problem. At last, I will compare the PPA difference of each algorithm. First, let's look at the benefit of pipeline. In this slide, I will define the maximum clock frequency a circuit can run at, and define the throughput for digital circuit. So let's see the circuit here and the waveform below. This is a simple circuit that does an AND function of two 64-bit signals. So the function is out A and B. Okay, simple. So for this circuit, if we assume the delay of this AND is 5 nanoseconds, so what's the maximum frequency the circuit can run at? And to simple the analysis, we just let the circuit to Q delay to 0 and the setup hold requirement for DFF to 0. So you can get the answer from the waveform below. This is this waveform here. Out underline W. Wire. Yeah, in the actual circuit, you may see there is 5 nanosecond delay after the rising edge. So the value here, the value of AND will stable after 5 nanosecond. So you can see if the period of clock is less than 5 seconds, such as 4.5, yeah. So the rising edge is here. Yes. So for this different flop, it can't capture the right data. Yes. Then you can get the answer. The period of clock must be larger than or equal to 5 nanoseconds. Yes, 5 nanoseconds. Then it will just catch the right result here. You will get the answer that the maximum frequency should be 1000 divided 5, then yield 200 megahertz. Yes. So this is the maximum frequency this circuit can run at. And if you just look at the waveform from the Arbiter simulation, you may see the waveform like that. This is because in Arbiter simulation, the AND is low delay in Arbiter simulation. Okay. But in actual circuit, as we have explained in the first chapter, the compilation logic will have delay. Okay. So what's the throughput? What's the throughput for this circuit? The definition of throughput is how many jobs can be done in a given time, usually in a second. And throughput is usually equal to the maximum frequency multiplied efficiency. What is efficiency? Efficiency is the percentage of active cycles. For example, if you can give new data for every cycle, so the efficiency is 100%. And if you can just give a new data for every 2 clocks, so the efficiency is 50%. Yes. And if you can give data for if you can give 3 data for every 4 clocks, then the efficiency is 75%. So for this circuit, we can give data for every cycle, so the efficiency is 100%. So and multiply the maximum frequency, so the throughput here is 200 megabit of data. Yes, 200 megabit of data. Okay, so in this slide you can understand how to estimate the maximum frequency for a circuit and how to calculate the throughput of the circuit. And you must note that for the calculation of maximum frequency, this is just a rough equation. For detailed calculation, please see chapter 4 of this course. That is in the static timing analysis. Okay, let's see more example of throughput calculation. Let's assume we have to implement this function. The output equal to LUT and B. LUT is a lookup table. So you give an input and look up something from the LUT. Yeah, just something like a SRAM. And the function LUT is also very simple. It just increase the input by 1. The value here is A. The value here of the LUT is A plus 1. Okay. So let's assume the delay of the LUT is 2 nanoseconds, and the AND here is also 2 nanoseconds, and we assume the CQ to Q delay to 0 and the setup hold time to 0. So what's the maximum frequency and the throughput for this circuit? So the answer is the total delay is 4 nanoseconds, then 250 megahertz the clock can run. And you can see from the circuit you can change data for every cycle. Yes, from the waveform you can get the answer. You can change your new data A and B for every cycle. The next cycle you will get the result. Yes, this is the result after lookup, then AND together yields 2. 1 and 1 AND together yields 4. So the efficiency for a circuit is 100%. So you will give the throughput of 250 megabit per second. Okay, that is simple. And can we use some method to increase the throughput? Such as, can we increase the clock frequency? If you want to increase the clock frequency, you have to smaller the combination logic delay. So one method is insert some DFFs between the combination logic, then divide the large combination logic to small delay segment, to small segment, then each segment will have smaller combination logic delay. So the key point is here. The register will inserted into the combination logic. And we call this is the pipe register. Pipe register. So after the insertion of this register, the frequency can be 500 megahertz. That is doubled. Yes, it's doubled than the last circuit. It's doubled. And let's check the waveform for this circuit. This is A. Then this signal. You will get the result of LUT one cycle later. So when A is 0, you will get the LUT result of 1 cycle later. Then you add together the two add together yields 3. But the result we expect is 1 and this is the LUT result. Yes, and plus 1 yields 2. Yes. This is what we expected. But the result you get is 3. Yes. For the first input 0, 1, we want to yield 2. For the second input 1, 2, we want to yield 4. But for this circuit, after inserting the pipe register, input 0, 1 yields 3, input 1, 2 yields 5. So this is a bug. There is function bug after insertion. Can you tell where the problem is? And how to fix the bug? Okay, you can pause the video and I will go on. Please note that actually by inserting one pipe stage DFF, we can't double the frequency. It should be a number smaller than the doubled value. So you can get the reason from the STA course. Okay, if we want to try to solve the problem, one method we can choose is lower the toggle rate. That is, we just change the input for every 2 cycles. Yes, 0. Then after the cycle we get the LUT value 1. Then the 2 add together yields 2. And there may be a garbage value here. We can just discard it by adding a valid signal. Yes, you can valid a valid signal to indicate which value is valid. Yes. Then the input 1, 2, 1. Then get the LUT value, then add together yields 4. But by doing this, you have decreased the efficiency to 50%. Although you have doubled the clock frequency, but you have decreased the efficiency, and when they are multiplied together, the throughput is still the same, 250 megabit. You make the circuit more complex, but you didn't get anything. So this is not a good solution. Then how about this one? The problem is after the insertion of pipe register, the LUT value here is delayed by 1 cycle, and we want to use this one to AND with this one. Yes, so we just need to add another pipe register and the data path of B and delay it for a cycle. So this is the B delay. Then the two will be aligned. Yes, the two will be aligned, and then we add them together to yield 2. And this is also true for the second input. The value A, 1 cycle later, we get the LUT value here. Then we delay the input by 1 cycle here. Then add them together to yield the value of 4. So in this circuit, you can see the maximum frequency is still 500 MHz and the efficiency is 100%. So we'll yield the throughput of 500 megabit, which is double of the initial circuit. Yes, this is the initial circuit. The throughput is 250. Okay, from this simple example, you can learn two things. One is sometimes you may lower the toggle rate, or you can say lower the efficiency, and get the correct function. The second is, if you want to pipe a design, you have to add pipe registers on all the data paths, such as the data path of B and the data path of A. You have to add pipe register to both the paths. That is, from each input to the output, they will have the same pipe latency. For this example, from the value A here, from the value A here, we will have 1 stage pipe, then 2 stage to and the output. And for B, for all the input, you will have the same pipe latency. So this will be the first pipe, then the second pipe. For all the inputs to the output, the pipe latency is the same. Then you can maximize the efficiency of the circuit. Okay, that's all for the benefits of pipeline, and you can understand why pipeline can increase the throughput of a circuit. We insert pipe stage to small the combination logic delay, then increase the maximum clock frequency while keep the efficiency of the circuit. As we have increased the maximum frequency, so the throughput will be increased. Okay, let's take a break.